Autism.
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 Dramatic rise in autism cases.
Autism. You often hear about it in the news. Autism is the colloquial term for autism spectrum disorder, abbreviated ASD. It is the fastest growing developmental disorder in the United States, and it's estimated that 1 in 68 children in the US will be diagnosed with some form of autism. So what is autism? Autism is a neurological condition that affects the way a person interacts and experiences the world around them. Its core symptoms include delayed and disordered language, impaired social interactions, repetitive behavior, and a restricted range of interests. Its associated symptoms include immune dysfunction, sleep disturbances, and GI symptoms. Sadly, despite its growing prevalence in the United States, no FDA-approved pharmaceutical treatment exists. However, there is hope. The human microbiome, which is the collection of bacteria and viruses that live on and within us, has arisen as a potential target for therapeutics for many disorders. Over the last decade, we have learned that these microorganisms have many beneficial roles within our body to promote a healthy, functioning body. The gut microbiome, in specific, has many vital roles, ranging from extracting energy from our food, to regulating our immune system, to protecting us against disease-causing microbes. So given their vital role, alterations in our gut microbiome could potentially lead to gastrointestinal disorders. However, more recently, they have found that alterations in our gut microbiome can be linked to neurological conditions. One such neurological condition is autism spectrum disorder. While its core symptoms are neurological, one associated symptom, GI symptoms, are found in 70% of children with autism. And these GI symptoms range from chronic diarrhea to chronic constipation. Interestingly, these symptoms correlate positively with the severity of autism. So what does the gut of children with autism look like then? Children that have autism tend to have been prescribed oral antibiotics between the ages of 0 and 3. This may account for why many studies have shown that children with autism have a different gut microbiome than their neurotypical peers. This is characterized by a decrease in the overall diversity in the bacteria in the gut and a decrease in the number of fermenting bacteria that are important for glucose metabolism. So given the altered gut microbiome of children with autism, our hypothesis was that changing the gut microbiome of ASD children may alleviate GI symptoms and potentially mitigate the other core and associated ASD symptoms. Fecal matter transplants, or FMT, have arisen as a major way to alter the gut microbiome. Fecal matter transplants are when you take the gut microflora of a healthy individual and transplant it into an unhealthy individual. This has been extremely successful with a single dose for treating C. diff infections and other gastrointestinal disorders. However, a single dose of fecal matter transplant has not been successful in treating the GI symptoms of children with autism. As a result, our team developed the Microbiota transfer therapy, in which we give children with autism the broad-spectrum vancomycin antibiotic to clear out the gut during the first 2 weeks. We follow that up with a single high dose of fecal matter transplant, then followed with daily small doses of fecal matter transplants. These small doses of fecal matter transplants were given in the form of a chocolate smoothie. And as a result, I can never look at a chocolate smoothie the same way. We recruited a total of 18 autistic subjects aged 7 to 17 with moderate to severe GI symptoms and with moderate to high neurocognitive functioning because we wanted the kids to be able to understand that they were undergoing treatment. We also recruited 20 neurotypical age-matched controls with no GI symptoms. Throughout the course of treatment, we collected stool samples to be able to monitor changes in the gut bacteriome and virome, so that is the collection of bacteria and viruses within these children. We collected samples at the beginning of the study, after the vancomycin, at the end of study, and 8 weeks later to see if there were any long-term effects. It's important to state that this was an open label study, meaning that the participants and the researchers knew what treatment was given to each individual. Throughout the course of the treatment, we monitored the GI symptoms and the overall autism symptoms through questionnaires to the parents and to the physicians. Because our main goal was to alleviate GI symptoms, we quantified a response to treatment by a 50% reduction in GI symptoms through the course of the treatment. And that was, again, using this questionnaire that we assigned to the parents. So what did the gut bacteria look like following MMT? If you recall, pre-treatment, they had a decrease in the overall bacterial diversity and a decrease in the number of fermenting bacteria. Following treatment, what we saw was an increase in the overall bacterial diversity that matched their neurotypical peers, an increase in the number of fermenting bacteria, and the successful transplant of donor bacteria to the children with autism. But what about viruses? Viruses play an important role in the gut microbiome, but they've been largely understudied. Recently, what we found is that 23 core viruses exist within the healthy gut phagum, indicating that these viruses are most likely important for a healthy functioning gut. Furthermore, it's been hypothesized that gut viruses can provide a non-host derived immunity, meaning that they'll line our epithelial walls and wait until a pathogenic bacteria comes in which they can attach to and kill before it can impact our health. In addition, they've been found to be able to replace the beneficial function of commensal bacteria. Commensal bacteria are the beneficial bacteria that line our intestines and protect our intestines from invading pathogens. So what they found is when they cleared the gut of beneficial bacteria and then replaced them with an enteric virus, that enteric virus could provide that same beneficial role as the commensal bacteria. So we wanted to look at what did the viral community look like in these children with autism. So we were able to sample 50 viromes in total. So we tracked 4 autistic individuals across the course of treatment, and I sampled an additional 8 at the beginning of treatment and right at the end of treatment. And then we also looked at our neurotypical subjects as well. Because we knew nothing about the gut virome of children with autism, we first wanted to see how did it differ from their neurotypical peers. Interestingly, we saw no significant difference in diversity in the viral community, like they saw in the bacterial side. But we wanted to see how did these viral community change following the course of treatment, or throughout the course of treatment. If you recall, there were responders and non-responders. When we look at the responders, the diversity does decrease following vancomycin, as we would expect, but throughout time, it recovers. If we look at the non-responder, it does not recover with time, suggesting that MMT helps with the recovery of children with autism following vancomycin throughout this treatment. We then wanted to see, did these donor viruses from the MMT transplant transfer to the ASD subjects? And what you're looking at here is each bar graph represents a different autistic child that we sampled. On your y-axis is the percentage of the community. The different colors represents where did that portion of the viral community come from. All of the blue represents that it came from the donor fecal matter transplant. And so what you can see is in every single individual, we saw a transplant of donor viruses. So following that up, if you recall, we saw no differences pre-MMT between the neurotypical and the autistic children. But post-MMT, what we saw is the recovery of diversity following vancomycin in the responders and the successful transplant of donor MMT viruses. So how did this impact the GI symptoms? Because that was our original goal, to alleviate the GI symptoms. What you're looking across your y-axis is the progression of treatment. And on your x-axis is the progression of treatment. And on your y-axis is a measure of our GI symptoms. What you want to see is a decrease. And that represents an improvement of GI symptoms. And what we see through the progression of treatment is a significant decrease in the GI symptoms. So what happens to the overall autism symptoms as a whole throughout the treatment. Here, again, you're looking at the progression of treatment on your x-axis, and then your y-axis, you're looking at how did the symptoms improve. And here what you're looking at is an improvement is an increase in value. So throughout the course of treatment, you see an overall significant improvement of autism symptoms overall. So given the success of the transfer of the donor bacteria and viruses and the improvements in GI symptoms and overall autism symptoms, we now want to move to a double-blind experiment where we have more participants and can follow the individuals over a longer course of time. And our ultimate goal is to get this approved by the FDA for the treatment of GI symptoms in autistic children. So I just want to conclude here saying that this was a team effort with collaborators across Arizona State University, Northern Arizona University, University of Arizona, and Ohio State. Thank you very much.